Thank you. So my presentation could not be more different. So I'm a mechanical engineer. I'm also a licensed architect. And I'm here to tell you that all your creative designs are, in fact, can be boiled down to a couple parameters. And we've already modeled it. We already know how it perform, all the creativity. I'm going to talk through how we're taking large data sets across 3 different scales. And again, I'm a mechanical engineer. I'm like EUI, peak load, ice chillers and pumps. Like that's my day job. So I'm going to talk a little bit about early concept, modeling, some of our detailed design modeling, and then some of the stuff that we're doing in existing buildings. When we talk about decarbonization, I don't actually care about your new buildings. They're great. Code will make them pretty good. Even if you want to do whatever you want, the code will make them good. In 2050, all the buildings that exist, 90% of them are already here. And they all suck. So existing buildings are actually the crux of decarbonization. So all the new design, great, but let's see how you tackle existing buildings. So I'm going to talk about large data sets. The first project, oh wait, I need to start my timer so I don't get yelled at. Hold on. All right. So the first project was a joint collaboration with the Department of Energy through Oak Ridge National Lab. We do a lot of our R&D work for large data in partnership with Lawrence Berkeley Lab, Oak Ridge National Lab, and NREL in Colorado. Leland Curtis was on our team. He has since left, but he was deeply involved in this large data set project. So one of the issues that I think was brought up earlier is the sequential idea of design. You're going to make something, then you throw it over the fence to an engineer or a building performance analyst, and you're like, how did it perform? And then it takes 2 weeks for that person to build what you just built in their tool, and then come back to you to be like, it didn't do well. Yeah, that's not going to work. And then by then, you've already gone past that design by like 8 weeks. And if you're drinking soda and going all night, you don't even remember making that building. So we kind of wanted to blow up that process. And we decided to take on the challenge of modeling every building that our firm could ever build. So rather than wait for you to design it, we decided to pre-simulate it. So we took some phenotypes of, if you sort of boiled our design down to their core essence, the components that impact energy, we came up with a data set, and it's really a metadata set. There's a bunch of variables buried in here, but they can kind of be summarized or boiled up. We looked at every climate zone that we do work in across our firm, which ended up being all of them. The scale of which we build. So typically, we're doing hospitals, labs, higher ed, office buildings, whatever. So we did a deep survey of all of our work in the history of the firm. Where is it? How big is it? What types are it? Well, let's model it all. Unfortunately, when you look at every permutation of that set of data, it's 4.7 million different models. My team is not large. We have about 22 people. And assuming that I could model each of those buildings in 2 minutes, it'd take me through the end of my career. And that's assuming I could model it in 2 minutes. If you actually look at bespoke models that you're handing off to your engineer, they're like, oh, I can do that in a week. And they're like trying to look at your Rhino models. They don't know what Rhino is. They're like, even with translation software, they're all struggling. So instead, we took the approach of what if we could do a sort of a randomly selected process and use AI for a surrogate modeling process. So we did 256,000 models, and we were able to do them in about a second per simulation. So this is where having friends at a national lab are great because they have supercomputers. Like you guys, like we all talk about cloud computing, that's awesome. I'm talking about the buildings or the computers underground that you have to book 9 months in advance, and then you get 72 hours. So we're like, what can we do in 72 hours? And that's how many models you can build in 72 hours if you use the automated scripts from AutoBIM, which is a suite of tools that were developed at Oak Ridge National Lab. So we built 256,000 models in 72 hours, which sounds really short, except for the 9 months that it took to get to this point, so that we knew what we were modeling, the parameters that were going to go into it, the spread, all the analytics on our building stock in terms of essentially the bumper bowling of energy modeling, like what are the bounds of the question. So it took us quite a bit of time to do that. Our goal, though, is trying to get to that 4.7 million, every permutation of everything that Smith Group could ever build. So through the surrogate modeling process, we used a random forest surrogate model. Again, we modeled key points and then let the model fill in the rest of the data set so that we didn't have to do that real time. We ended up, there's a lot of different surrogate AI tools that you can use to build out your data sets. For us on this particular quest, the random forest methodology gave us the best tightness to the model results versus predictions. And what we wanted to come up with was being able to take this massive data set and essentially build something inside the design tools that our teams are using that would smack them across the face when you do something wrong. I want you to be creative. I want the architect to still have agency over the question, but I want to keep them bounded so that they don't exceed our net zero goals. We can achieve net AIA 2030. We're looking at carbon metrics. I actually care more about peak load than EUI, and I'll talk about that in a little bit when we do existing buildings. And so being able to test sensitivities across the entire spectrum of what we could build is kind of taking that 30 years of industry experience where somebody's like, well, I've been doing this forever and that won't work. Well, now it's sort of built into the tool, and so it can guide you through the space. Let's see if this will, yeah. So we've taken all that data set, and that's actually built into sort of an input. This is all hidden from the architects because it turns out that nobody thinks their building looks like this, and they don't respond to it. You know, they're like, well, that's a big dumb box with a ribbon window. My eyes are offended. We can actually boil down your design into something that looks very similar to that in terms of energy performance. So there's a skin that hides that, and it shows what you're doing, and you're amazing, and your creativity is robust. But we're actually looking at how it's going to perform as something underneath. And if you go outside the characteristics that we need to hit our targets, it's kind of going to bump you back. So it's a guide. The thing that all the optimizers out there fail to think about is that as soon as you fix one element, the sensitivity of all the other ones change. If you fix a window to wall ratio, all of a sudden our value for your opaque facade, the importance of that changes. So there is no optimum design. You're wandering, and we're just trying to keep you so that each time something does get fixed because you want it to, then we're going to say, well, this is what needs to happen to sort of keep you on track. So how does that then go in? Because the next question that we get is, oh, that's great, but what about this? And it's a hyper-specific question. Like, should my mullion be that big or that big? Well, I did not model that in the 4.7 million options that we now have access to. And so within the design space, so if we think about those 4.7 million options, it's like looking at architecture with fuzzy glasses. It's pretty good, but it's not answering the exact spacing of a mullion, a shading, a frit, all the sort of detailed questions. And so as long as we're using the same phenotypes, we can now look at detailed questions and add that data set into the same model. And so it's almost like taking a really big model and you're looking at big ideas and then zooming into a quadrant, peeling back and starting to look at some detailed questions. And in the third case, I'll show you how you peel that even back and you get terrorized. But the idea here was how do we start to optimize a facade through detailed iterative modeling. This can be generative if you so choose, or you can rely on the design team. In this case, this was integrated with a panelization company that we were working on because we were trying to reduce costs. We were trying to do a net zero, mixed use, high rise laboratory that was all electric and met the budget. So things wanted to be bespoke, but nothing could be bespoke. Everything needed to be like off the shelf. This is so simplified, but all of you guys have been talking about how the data moves around. This happened to be that process because we needed to kick something out that can go out for pricing. And we can talk a little bit about more of that. Anybody who's been doing parametric models already knows sort of this iteration. But the thing that I wanted to share is, in this case, we ran another 1,000 models. Those 1,000 models, when added back to the big data set, is this detailed blip inside. And if I have enough of those, if I start adding all these bespoke questions that I'm asking to this larger data set, I can start to pick up trends and start feeding in some detail into what is otherwise a pretty gross estimate of energy use. Essentially, in this process, there were a couple different multi-factor optimizations that we were looking. And again, I don't typically actually care that much about EUI because it doesn't cost money. costs money to operate, it costs carbon to operate, but it doesn't, EUI does not cost you to build a building. Peak load does. Peak load is how big your chiller is. It's how big the ductwork is. It's all the things that nobody in this room probably cares about, but it's the entirety of my job. That's where the money is. And so in this case, we're trying to define sort of the best case iterative combination of options that would reduce peak load, meet the usable daylight index criteria that the client had set out for the project for sexy, engaging, daylight, indoor, outdoor, love fest. I'm in the background saying, how big's my chiller? How big's my chiller? How big's my chiller? And so because we have so many factors, we can do multi-factor Pareto effect and kind of find the edge of how far we can push against. But at the end of the day, we're not telling you exactly what to do. There isn't an optimized answer. There is a whole cluster of options that you can work within that are fine, at least from an energy standpoint. So the last thing that I want to hear, or that my team wants to hear, is from an architect, it drives us insane, is what's the best option? There isn't one. And it's going to blow everybody's mind, but there's a whole cluster of options you still get to actively design. So integrating that into the process, our tools, just like everyone else here, it's a whole suite of things, and it's all about data management. The most successful thing that we've done is integrate with our firm-wide data folks. We've hired data scientists in-house to build these complex models. But that's probably the most important thing you can do, is hiring people who understand how to move and hold and access data. So this is one of the tools that's sort of built out from that. Again, a lot of this is hidden so that the actual designer doesn't have to know any of this stuff, but it helps us navigate performance criteria. So the last question, with my 4 minutes or 3 minutes left, is what does that mean in the future where, and somebody else mentioned it, the grid is changing, we're trying to decarbonize, we're trying to do all this amazing work, and I just optimized a model for like 1 day or 1 year, a fake year that doesn't exist. So we've moved into looking, I would say, at an optimization at a much larger scale for existing buildings. So with one of our key client partners, which is Kaiser, we do a lot of work at large hospitals, including setting up templating for their entire sort of acute care line. We got under contract with them an agreement that we would have access to every control point in every facility that they have for a multi-year period. So this is not sexy for architects, but for engineers, this is like a data dream day. We now have about 84 million records. I can tell you the position of every valve controlling every VAV box in their facility pre-COVID, during COVID, post-COVID. We have access to card swipes for occupancy. We have their OR scheduling. We have more data than you can manipulate. So when I said hire a data scientist that can hold data, organize data, access data, 80% of my budget for this project is in data. 20% is what can we ask the data? Data, data, data. It's the most important thing that we have. So the only question the client actually asked us was how big should our chillers be in our new hospitals? Which we could have probably answered with less data. But since I had access, I'm a kid in a candy shop. I want it all. So we actually analyzed every room type across their facilities, did a whole bunch of statistical modeling based on real world data sets. So nothing here is a surrogate model. This is measured data over real time. Turns out it's nothing like our predictive models that we use for code compliance, that we use for Energy Plus. They're horrendously wrong and generally overestimate load demands. So essentially coming out of all of this, we were able to say with confidence, because they template their hospitals, we know what climate zones are going, that they could spend 20% less on their HVAC system than they are doing now and still have resilience built in for climate change and temperature changes. 20% savings on their next billion-dollar hospital paid for this project and then some. So when we talk about cost transfer, where's the money? Save money in construction and get people to pay you that money to provide a value. Like they didn't pay me hourly, they paid a value, which hourly turned out phenomenal. So being able to do that analysis is quite important. And the next thing that we're using that data set for is looking at changing the way that we think about optimization. In energy and in carbon, everybody's been asking, like, what's my EUI? Am I carbon neutral? I'm like, great, we can answer that question. The question is that we should be asking is, how flexible is my building? How can I shift load? How can I squash load? How can I move load? How flexible can my building be? And because we have the data set, we can now test through essentially building model-based optimizations on our data set. We can test how flexible that hospital could be to a future change in carbon pricing. What if I added a carbon tax in the middle of the day? What if I said I need to lock out some system from 4 to 9 p.m.? I have a data set that I can build a model on that I can make a damn good estimate of how that building would perform. The accuracy of that model is incredibly important because now if we execute on those optimizations, the client can aggregate that response to a grid event and monetize it. If across an entire hospital portfolio, say 1 billion square feet, if they said at a moment's notice, California or Texas, let's make fun of Texas because I'm in California. Texas, you're gonna have a grid event because you're having a heat wave. What if I could tell you with certainty how my building would perform if I locked out during that critical peak time? How much load can I shift without impacting operating room temperatures? We have a model that we can test that because we have the data. Access to these data sets is incredibly important. And so the future isn't in, it's not in finding that one net zero and how much PV do you need? That's a great question, but it's like elementary school for the questions that we can ask these data sets. So my time's up. We did publish for the large scale data set our methodology and the results, and those 4.7 million models are publicly available because we also are open source. So in the link to the article and in Journal of Building Engineering, we have the host site for the data. Run with them, optimize them, find holes, blow it up, do whatever you want. Thank you.